All right, good morning, chemists. Let's get started. So plan is today is start a little bit of chapter 15, and then the second half of class we'll do midterm review. Is this working? Yeah, okay, all right. Some announcements before we get started, but these are the same ones as previously from Tuesday. Please test your lockdown browser. There's still like a third of you who haven't tested it, all right? We're doing our exams in recitation. I can't be there at all those recitations. So this is my, the best bet for me to ensure that everyone can start their exam in the recitation space. So that lockdown browser ensures that everything's set up correctly and that you're accessing everything correctly. Please test that before the exam. I'm going to start sending angry emails to people who haven't tested it out. And if you took 1210 here, don't assume that it works, all right? Never assume, just test it. It'll take just a couple minutes. My review session was recorded and it's already posted if you want to check those out. But at this point, since we only have a day until our midterm exam, I suggest one of the 4 practice midterms. Is where you should be headed there. Do a practice exam under exam-like conditions, see what questions you get wrong so you can focus on those concepts for your next round. Or, if you want to study a little bit, that's how you use your time effectively. Study the things you know you don't know. If you know you can get these other types of concepts right, there's no point in studying those. All right, so study. And then midterm 1 is during recitation for the majority of you on Friday. Make sure you have that approved calculator, some type of writing utensil for the scratch paper that you'll be given, a photo ID so you can prove your identity, a device to duo, so like your phone or whatever. And then keep in your brain your OSU password because Respondus does not autofill. All right, and then the last thing, also if you didn't hear, I will do a large GE launch interview thing next week, next Tuesday at 5:30. I put it in your calendar, so let's worry about it till after the midterm. And lastly, and I didn't mention this in my other class, if you can't get access to the exam materials, like if you're trying to get the exams and it says it's locked, it's because you haven't done everything in the lecture resources. You need to make sure that you have all check marks, and then once you do, then you'll get access to the exam resources. So if there's any red thing, it means that all those practice midterms are locked for you until you do all of it. So do check that out because I got a couple emails about that. All right, so any questions about our exam? Are we excited? Yeah, maybe. 20 questions, 50 minutes for the majority of you. All right. So plan is to start chapter 15, get about like 10, 12 slides into it. I'll tell a really morbid story, and then we can do midterm 1 review. Okay. Now you're anxious. What's the morbid story? Yeah. Yeah. So the question was, do students finish in a right amount of time? I don't know, because I've never done recitation midterms before. But if you just do the calculation, how many questions were our exams last year? Do you remember? Like 30? Okay, so 70 minutes divided by 30 is 2.3 minutes per question. So now we have 50 minutes, and it's 20 questions. That's 2.5 minutes per question. Does that help? Okay, all right. Okay. So that means more time per question, but this material is harder. All right, so let's talk about chemical equilibria. So I mentioned this class, Chem 1220, is the class about K. We talk about K forever. We just talked about what kind of K in chapter 14? Rate constant. I called this small k, baby K, little k. Rate constant was related to reaction rate, right? Rate equals rate constant times concentrations of reactants and so forth, right? So rate constant was related to the overall rate of your reaction. So those two were related to one another in Chem or in chapter 14. They don't necessarily mean the same thing. We can have a reaction rate and we can have a rate constant. Those are different things. And then finally, what this chapter is kind of bringing these ideas together, and now we're going to talk about equilibrium constant, big K. Big K, so we're graduating to big K, where we will talk in great detail the nuances of elementary reactions. Okay, so let's gauge ourselves. So in this chapter, we're talking about chemical equilibrium. So what is this? This is, I'm going to basically just say, is a new type of reaction. All right, so up until now, we have only studied irreversible reactions. What that means is, remember I do the hydrogen balloon experiment thing, the demo, loud, boom? When I do that balloon, when I blow up that balloon, is that reaction reversible? No, right? The hydrogen reacts with the oxygen to make water, and that's it. And then it's done. Once we make all that water, we're done. So that's an irreversible reaction. I can't go backwards. But in this chapter, we're going to talk about reactions that are reversible. And we actually already kind of talked about this already. We already talked about fast reversible reactions in chapter 14 in mechanisms. Remember how we got rid of intermediates? We used the fast equilibrium step. Well, now we're going to go into an insane amount of detail about that fast equilibrium step. So we've moved on from irreversible reactions. Irreversible reactions used just like a regular arrow, like a regular one direction arrow. But equilibrium, and that's what we're going to talk about for like the next 3 chapters, uses a different kind of arrow where there's a forward and a reverse direction on that arrow. We call this an equilibrium arrow. And it's the idea of, hey, actually both sides of the reaction exist at the same time. We don't consume all of our reactants to make products. We actually have both sides of the reaction at the same time. Remember in 1210 when we talked about weak acids and weak bases? These substances, do they fully ionize in water? Weak acids and bases? No, that's only strong acids and bases. So a weak acid only partially ionizes, meaning that there's some neutral molecules, some ions in solution. It just partially ionizes. And this is due to the idea of chemical equilibrium. Both sides exist at the same time because the forward and the reverse reaction happen at the same time. So when we have a system at equilibrium, as the observer, we're the observers, right? We're just the surroundings. We watch the reaction, which is the system. When we look at a system that's at equilibrium, to us, it looks like it's not changing, that it's staying static. Concentrations aren't changing. That's what we see. But on the particle level, things are actually changing. That the forward reaction is happening, but also the reverse reaction is happening at the same rate, so there's no net change. So we don't see any like big changes in concentration. An analogy would be like if this person was walking up a downward escalator, the escalator has a certain rate in one direction. And if the person going up the escalator matches that exact same velocity, that exact same rate, the person doesn't move. As the observer, if we're looking at that weird person walking up the down escalator from far away, they're not moving in space, but they do have a forward rate, but it's being canceled out by the reverse rate of the downward escalator. So we don't observe any net changes, but a reaction is occurring. And that's the idea of chemical equilibrium. There's no net change, but the forward and the reverse reactions are occurring. Okay, so chemical equilibria. So we have our reactants, we have our products. The new idea here is we have this new kind of arrow that indicates reverse reaction and forward reaction are happening, right? So it's this double arrow. That's the new idea here. Okay, so the definition of chemical equilibria. A system has achieved chemical equilibria when the forward rate equals the reverse rate. When the person walking on the escalator or going down the up escalator or whatever they're not moving in space. That's when chemical equilibria has been achieved. And sometimes it takes time for that to happen, right? And so what's special about different reactions is they have certain equilibrium constants that describe the concentrations of reactants and products at equilibrium, right? It's an intensive property that we'll look at in a little bit. So this K value is a unitless number, unitless value. And all it does is tell us the ratio of products and reactants at equilibrium. Every different reaction has a different K. Even a reaction at different temperatures will have different K, and we'll explore that in a little bit. So how we read K, it's just a number, all right? Big K is just a number, and there's no unit, thank goodness. There's no unit, okay? Because our other K, does little k have a unit? And does that unit change sometimes? Yes, it does. But big K does not have a unit. It just tells us the relative ratio of reactants and products at equilibrium, where it is product concentration over reactant concentration, and there's usually exponents. And thank goodness the exponents, yes, they do relate to the stoichiometry. Yes, okay. So there's two types of Ks. All right, so since big K talks about relative presence, relative concentrations of things at equilibrium, we can use two different types of K, Kp or Kc. The difference of these two Ks is what unit are you using to talk about concentration. That's the only difference. Kp is very important for gases because gases have pressures. And we talked about this before, pressure can be a concentration unit. So if we put pressures in for products over reactants, we calculate Kp, right? So use pressures. Versus Kc, C stands for concentration. So we use molarity instead, all right? So use molarity for things that are aqueous or gases as well, because a gas can have a molarity, a gas can also have a pressure as well, because pressure equals, if I rearrange Pivner, pressure equals N over V, which is molarity. So that's a small detail, right? So Kp use pressures, Kc use concentration. All right, perfect. Products over reactants. Okay, so let's look at the details here. I mentioned that K, you'll have a different value of K for every single reaction. K is an intensive property, I mean it's specific to the reaction. It doesn't actually matter how much stuff you have present. But K is temperature dependent, and we'll look at that later. So I want to show this example of a reaction that I do and some interesting things that kind of come up during this reaction. So I take all of this, these are gases. I take a hydrogen molecule, an iodine molecule, they react and make HI. Cool. And this is an equilibrium. So I have a number of experiments here, and what you see is some initial conditions, and then you see some equilibrium conditions. So these initial conditions are what I shove in my reaction vessel initially. Those initial conditions are let to settle and react with time, and after a certain amount of time, we let that reaction come to equilibrium, and we see some changes happen. So let's look at those changes. So in this first reaction, reaction 1, experiment 1, what's in my reaction vessel? H2 and I2. What are those in the actual reaction? They are what, reactants or products? Reactants. So let's predict this. Don't even look at what happens later. Let's just predict this. If we only start with H2 and I2 in our reaction vessel, which way does the reaction have to go? Forward, towards the products. Yes, we have to make some products because all I have are reactants. And that's exactly what happens. That you see that the amount of reactants decrease, all right? Some of the reactants are consumed, and at the same time, some product is made, all right? And so what's interesting here, and where equilibrium constant comes from, is we take the equilibrium conditions and concentrations we just calculate, we plug those into our Kc expression, and a number will pop out. All right, a unitless number will pop out. So let's quick just write the Kc expression here. It's going to be products over reactant concentrations, but your coefficients, your stoichiometry becomes exponents. So product is HI. HI, what's the exponent? 2, yep. And then H2, concentration, what's the exponent? 1, or you can just put nothing. And then I2, 2, an exponent of 1. And so that's what you see here in this last column. They took these pink equilibrium concentrations. So they did 1.5 squared over 0.2 over 0.2, and they got a number of about 52. All right. And so that describes the ratio of products over reactants at equilibrium. Okay, so let's look at the next experiment and see if anything is different. Okay, so in experiment 2, how would you describe the initial conditions? What are you shoving in your container? Only HI, and that is a what in the reaction? Product. Okay, so I'm only shoving products in the reaction vessel. Okay, but if we think about equilibrium, I only have products where the reverse and the forward reaction can occur. Which way does this reaction have to go? Backwards. It has to go backwards because it's an equilibrium. And that's exactly what happens. Some of the product is consumed, see it goes down, and then some reactant is produced. And you see they're the exact same numbers. If we shove those back into our Kc expression, look, we get 52 again. Interesting, all right? So then if we look at experiment 3, it's just like experiment 2, but instead we have half of the amount of reactant. So you might think, oh, my equilibrium concentrations will be different because I'm not starting with as much product. And that's true. The equilibrium concentrations are a little bit different. We still consume product and make a little bit of reactant. But the interesting thing about equilibrium constant is once we take the ratio, once we take these, yes, different equilibrium concentrations, do products over reactants, we still get the same number, 52. And that's why it's called equilibrium constant. You'll always get the same ratio of products over reactants at equilibrium for a reaction, right? Okay, so yes, basically, moral of the story, at equilibrium, products over reactants is the same value regardless of what you put into the vessel, regardless. Okay, the system will always change itself, so it'll get to equilibrium. Okay, so how did I get this Kc expression? Well, I knew it was Kc because it's concentrations. So that's one idea. Kc implies we want to multiply products over reactants using concentrations, and I need to then make sure that any exponents in my Kc expression come from the stoichiometry in the balanced chemical equation. All right, so yes, coefficients become subscripts with K, big K. All right, okay, so things with concentrations. So things that you put into the Kc expression, you want to put anything that's aqueous because, you know, things like molarity, things that are aqueous have a concentration, but you can also put gases into a Kc expression. You can count how many moles per volume there are of a gas sample. So you want to put both aqueous things and gaseous things in a Kc expression. What you don't want to include in your Kc expression are solids and liquids because those things don't really change concentration over time. So it's fine to leave those things out. So you might see in this equation, look, there's an E component in this balanced chemical equation, but does it show up in any of those K expressions? No, and it's because it's a solid. So we don't include solids in our K expressions. Also liquids, don't include those either. All right, because they do have concentrations, they're just not important. Okay, and so we see here Kc stands for concentration, use molarities, but we can also write a K expression for gases as well, but we want to use partial pressures instead for those components. You still use the exponents as typical. Okay, so where the heck did K, big K, come from? Why is it products over reactants? You actually already know why. We already talked about fast reversible equilibrium before in kinetics when we did mechanisms. So let me just expand on that a little bit. All right, so the definition of equilibrium is when your forward reaction rate is equal to your reverse reaction rate, meaning the rate law for the forward direction equals the rate law for the reverse direction. Do you remember doing that for mechanisms? Yes, you remember doing that for mechanisms. So it's the same idea here. So for an elementary step, an elementary reaction, if we write the forward rate law equals the reverse rate law, this is how where equilibrium constant comes into play. So let's pretend we have this reaction. A plus B gives us C to D. Let me write that out. A plus B, equilibrium, C plus D. So if we wanted to write the rate law for the forward reaction, we would use the reactants, right? Am I allowed to just take stoichiometry and make them exponents for these? Yes, because it's an elementary step. So that's what you see here. The rate law for the forward direction is KF A times B. All right, so the rate law for the reverse direction, I actually want to use the products. The products are now the reactants. So the rate law for the reverse direction of this reaction is rate equals KR, so rate constant for the reverse direction times CD. Okay. When we did mechanisms and we wanted to get rid of an intermediate, what we said is, okay, set the reverse rate equal to the forward rate. That's what we did. And that's what we're going to do again here, because that's the definition of chemical equilibrium, right? These aren't just static steps. No, they're happening at the same time. So what I'm going to do is set both of those rate laws equal to one another. And again, we've done this before in chapter 14. Right, and so that's what this is, right? Right there. I've set the two rate laws equal to one another. If this was an intermediate, we could rearrange things and replace our intermediate with something else. But I want to do something different instead. So if we take these two rate laws, and what I want to do is put all the K's on one side and all the concentrations on the other side. That's what I want to do. All right, so I'm going to divide both sides by KR. All right, so on the right side, KR cancels, and then I'm left with this KF-KR ratio, right? And then what I also want to do is divide both sides by AB. So what I'm doing is just moving all the concentrations on one side, all the rate constants on the other side. All right, and so with that, if I divide both sides by AB, AB cancels. All right, and so now you can see, okay, I have all my rate constants on one side, it's a ratio. I have all my concentrations on the other side, it's a ratio. And so what we see, look, what is this? Products over reactants. Yes, that's what our rate constant is. So this ratio of rate constants, of concentrations from our forward and our reverse reactions, this is products, products over reactants, is actually equal to that rate constant that I introduced at first, right? Products over reactants, that's how we get it. But we also get something else interesting that comes out. Yes, equilibrium constant is products over reactants, but what is it also, according to this equation, this ratio? It's also equal to the ratio of the rate constants, all right? So both of these ideas come out here, all right? Where it's not just products over reactants, but it's also the ratio of the forward rate constant over the reverse rate constant, right? It equals both those things. It's a constant. Okay, so let's look at this graph and see if we can't discern any information from it. Okay, look at this reaction. What kind of reaction is it? Exo, endo? Endo, exo. What's the sign of delta H? Positive, so it is endo. Perfect, all right. What side's more stable? Products or reactants? Reactants. Okay, so then if the reactants are more stable, what side dominates, you think? Reactants, yeah, because it's more stable. Okay, keep that in the back of your head. All right, so now let's answer these questions. Okay, in which direction has the smaller activation energy? Reverse, yeah, if you think about yourself, your little ball going that way versus going in the forward direction, you see, the hill's a lot smaller going in the reverse direction. So based upon that answer, Which one has the larger rate constant? Which one's faster? The forward direction or the reverse direction? Reverse. Yeah, the hill's smaller in the reverse direction. And do remember, our Arrhenius equation also predicts that. It's inversely related to activation energy. All right, so that means the reverse direction is faster. Okay, so now let's bring in our definition of equilibrium constant. Yes, it's products over reactants. But remember, equilibrium constant is also the forward rate constant over the reverse rate constant. So what can we deduce about this ratio? Is it a big number or a small number based upon the answer we just said? It's going to be a small number, yeah. Because we just said, equilibrium constant is forward over reverse rate constant. We just said that Kr, reverse, is large. So therefore, K forward is small. So that means a small number over a large number is going to be a small number. Yes, right? But what else so equilibrium constant, yes, is the ratio of the rate constants, but it's also the ratio of what? Products over reactants. So if we just deduced Kc is a small number and Kc is products over reactants, what does that mean is more present at equilibrium, products or reactants? Reactants, why? Why are reactants more present? Because we want a big number in the denominator to make it a small value. So see how all of these things are related to one another. Rate constants, the ratio of rate constants is also related to the present, what thing dominates at equilibrium, products or reactants based upon the magnitude of K, all right? So on the other hand, if I said, okay, K is a big number, what if I said K is a big number? What dominates at equilibrium, products or reactants? Products. So what does that mean about the rate constant? Which one has a bigger rate constant?
We are supposed to be taking our Chem 1220 exam right now, except for our TA didn't show up.
Oh, your TA's not there? Yeah. Can you go to the Gen Chem office?
Okay. Where's that?
It's Celeste 110.
Okay.
It's like when you go to lab, it's that,
okay.
the big fishbowl glass doors
okay.
thing. Yeah.
Thank you.
Yeah.
Sorry.
Yikes. Okay. All right, so K is big. What were we saying? What's dominant if K is big? Products. Okay, and then what can you say about the rate constants? Which one's bigger, the forward direction or the reverse direction rate constant? It would be if products are very present, then KF is going to be really big. So the forward rate constant is going to be big. Yes, okay. Yeah, their TA didn't show up for their exam. I mean, I can't help with that, but all right. Well, good thing they didn't come in during this slide. Okay, so this is my attempt at a history lesson, maybe an ethics lesson. I don't know. So we'll see. Okay, so we've looked at this reaction before. It's the combination of nitrogen, hydrogen to give ammonia. All right. So there's something very, very special about ammonia and its place in history. Back in like the 18th, 19th centuries, we're kind of on the cusp of the technological boom human population was low enough at that point that farmers, agriculture could support mankind, like the number of mouths to feed. But there was a problem. Farmers just couldn't keep up with the demand of food. All right, but the problem is that population was growing and growing and growing, and so we were kind of on the brink of this food crisis back in the 18th, 19th centuries. And the reason, and it's kind of funny, we look back on this, it's so common when you make a garden, like yes, you water it, but also you typically fertilize plants, like that's common stuff. But back then, they didn't have access to fertilizers, all right, like we do today. So there's kind of this law that says that the yield of food production or any chemical process, you're always limited by the limiting reactant. Doesn't that sound familiar? right? So back then, the limiting reactant for agriculture was nitrogen. Not just any nitrogen, it has to be bioavailable nitrogen. Because if you think about it, where's the closest nitrogen to you? It's in our air, yeah. So it's in our air, N2. But N2, what kind of bond is between those two nitrogens? It's a triple bond, and triple bonds are really weak or strong? Strong. So plants have a real tough time breaking that triple bond in nitrogen. So yes, we have a ton of nitrogen in our air, but plants can't get it readily. So often what happens is farmers put fertilizer on their plants so we can get a boost of nitrogen to their root system that they can just drink up right away, right? But they didn't have that back then, right? Until Fritz Haber came around, all right, and basically solved that crisis for us and made nitrate-based fertilizers readily available. And he was the sole reason, and in his lab, one of the big reasons why population was able to skyrocket during this time, right? That's a good thing, right? Like feeding hungry mouths and fertilizers and agriculture, you know, increased crop yields, those are all important things. Right? Because of this reaction, he was able to take nitrogen from the air, hydrogen, optimize this chemical equilibrium, and make ammonia, which was then transformed to something else, where then it became fertilizer. All right. And they still use his same process today. Right? So he was the reason that you know, the world was able to increase their population so much. But there's always a but, right? Yes. So Fritz Haber was a German scientist during like World War I, World War II. And so in the same lab that he figured out how to, you know, make fertilizer for plants and essentially save the world, he also discovered chemical warfare and asphyxiating gases that they would put on the trenches and kill hundreds and thousands of soldiers all at one time in the trenches, all right, in the same lab. So not sure if that was equilibrium, but you know, he did have a part of that, you know, maybe with probably had a hand in gas chambers in during the Holocaust. So it's something to think about, right? Like he did this great thing of discovering the Haber-Bosch process to make ammonia that we're still using today, but then was also responsible for chemical warfare and changing the landscape of like modern war. By using gases and chemical agents. And so, I mean, like the question I proposed was, do you think Fritz Haber is a good guy or a bad guy? I don't know. I don't think there's an answer, but I think that's an interesting thing to think about, you know, and as scientists, we need to think about, you know, not just the numbers, but I think ethics. I'll only spend like 5 minutes on it, but, you know, like ethically, what does this all mean? I don't know. Everyone might have a different answer. You can jump down the YouTube rabbit hole about him. There's a lot of good stories. I don't know. Was he a good guy or a bad guy? I think if he didn't do it, someone else would have figured it out eventually. So that's what I think. But if you want to know a little bit more history about him, so he had a wife and a daughter. His wife begged him to stop after he started getting like recognition from like the German armies. His wife begged him to stop, and he didn't, so she killed herself. And then he had a son and a daughter, and the daughter studied chemistry. She became a chemist so she could find a cure for the chlorine-based gases, and she couldn't find a cure, so she killed herself too. Yeah, so I know, yeah. So that was the morbid story. Okay, yes. I just laughed because someone just walked in on that last part. Yeah, so that is Fritz Haber, so let's write out the chemical equilibrium for his reaction. Yeah. I like chemistry and history. I wish I was better at history and could tell the story better, but I think it's really interesting how big chemical, like even any invention or any discovery completely changes humankind's landscape. You know, big changes happen with big discoveries, and I think that's really interesting to kind of see when were those big discoveries happening through time. Okay, so let's write the Kc expression. Products over reactants, so what goes on top? NH3, but as what? Are we talking about pressure or concentration? Concentration, because I put C. So NH3, 2 of them. On the bottom goes N2, and then H2, there are 3 of them, right? So stoichiometry becomes exponents, and that's fine. Okay, so let's say bye to Fritz Haber. Okay, so we did the heavy lifting already and got the equilibrium expression. It's quite easy to do once you have the balanced chemical equation. So let's recognize that the expression that we just got, I'm going to just copy it down here because I'm lazy. That Kc expression is a value that describes concentrations of reactants and products at equilibrium. So if I tell you equilibrium concentrations, you can just go ahead and plug those into the expression to get the value of Kc. And because these are at equilibrium concentration, absolutely, we just put it into the expression. So NH3, and we do it, so put those concentrations in unadulterated. So for ammonia, it's 1.40 molarity squared. Even though there's a 2 in the stoichiometry, the 2 shows up in the exponent. I don't have to double the concentration or anything. The 2 is just in the exponent. The bottom, the denominator is 0.3 molarity, and then hydrogen is 0.9, but it is cubed, right? And I think if you plug that into your calculator, you get something like 9.0. And again, this is a unitless number. Yes, we multiplied and divided by a bunch of molarities, but we're just going to assume all those molarities cancel out. We're just trying to show the ratio of products to reactants. So it's a unitless value. Okay, so 9 will describe the ratio of reactants to products at equilibrium for this process at this temperature. So let's just ask it a little bit a different way. What is ammonia concentration at the same temperature, but I give you nitrogen and hydrogen concentration? So we already calculated Kc. So all we really need to do is use this same equation. We have Kc, we have nitrogen, we have hydrogen. We're just going to solve for the last, a different variable here. And so we can do this because we know what the K value is. And since the equilibrium constant always describes equilibrium concentrations, I can just go ahead, plug these 2 given values in. It should pop out what the equilibrium concentration of ammonia must be in order to maintain this Kc ratio. And so if you do that, putting in the numbers, it'll be 9.0 equals ammonia concentration squared, that's what I'm solving for, over 0.6 over 1.8 cubed. If you multiply everything on that denominator over with 9, I think you get ammonia concentration squared equals 31.5. Again, unitless, but know that when we calculate molarity out, that last number will have a molarity. So then I just square root both sides, and you do get that the ammonia concentration that comes out is about 5.5 molarity. All right, a 5.5 molarity is the value needed to maintain that Kc value of 9. If you want to check yourself, you can plug the ammonia concentration we just got, square it, and then if you divide it by the 2 given nitrogen and hydrogen values, what number should you get out? You should get Kc again. So if you plug all those values we just got back into the Kc expression, you should get 9, all right? Because it's an equilibrium constant that describes this one reaction. All right, so let's do 2 more slides, and then we will review. Okay. Okay, so in the previous slide, we talked about concentration. Things that are aqueous usually have concentrations, but gases can have concentrations too. And so when gases are involved and they're measured in pressure, sometimes it's easier to use Kp instead where we use pressures. But I'll remind you that molarity and pressures are related with gases. So when we have a gas sample, we can report it in Kp or Kc. But things that are aqueous, we can really only use Kc because aqueous things, salt, only have molarities. They don't have partial pressures, right? So a special thing for gases is that they have a Kp and a Kc, but they're related to one another, all right? They're not the same value, not quite the same value. And so we can use this expression to relate the Kc and the Kp for a gas sample, where Kp is the equilibrium constant when given in pressures, is equal to Kc when it's in concentration times a factor of RT. So R is the same gas law constant from Pivnert, T is temperature in Kelvin, and delta N. It's how the moles of gas change in the sample. I think it's easier if we just do an example rather than me just talk about it. So let's just do this example, and then I think we'll just finish up here. Okay, so let's convert between Kc and Kp for a gas reaction. So here is an all gas reaction. Gases can have concentrations or pressures. Here I'm telling you that the Kc, when I use concentration for this reaction, is 9.6. What is Kp at this same temperature? So if we think about it, I give you Kc, I give you T, R is a constant, so I just need to figure out what delta N is. And that's quite simple if you are given the balanced chemical equation. So delta N is how the moles of gas change in the reaction. So all you need to do is count the number of moles of gas on each side of the reaction. So how many moles of gas on the reactant side? 4. 4 moles of gas total. And then how many on the product side? 2. So we're going to take 2 minus 4 is equal to negative 2. So what that means is in the forward direction, this reaction loses 2 moles of gas. That's what it means. Right? But that negative 2 is going to go into the exponent that's up there. And then I think at this point it's just plug and chug. I got temperature, I got Kc, R is the gas constant, and then we put in delta N. So Kp, what we're solving for, is 9.6 RT, so 0.08206 liter ATM mole Kelvin times 573 Kelvin, and you'll take that to the negative 2 exponent. All right, multiply all those things together and you'll get Kp. All right, Kp also a unitless number, but recognize if it's P, it means we're using partial pressures in atmospheres. If we're talking about Kc, we're using concentrations in molarity. All right, okay. All right, so we'll end right there. Next week we will talk about